Hello everybody, this is the first lesson on numerical methods in Python. So this will be a series of videos, and today we will talk about linear algebra, and we will talk about how to solve linear system using Gauss elimination method and LU or lower upper decomposition, and yeah, these methods we will talk about, and we will show some examples, and we will focus on the code implementation of these methods in Python. And besides showing the raw codes, basic codes which I've created following this book, I will also show how Python itself has some built-in functions which solves the same problem. Okay, so let's go to, let me show you what I will talk about. We will talk about this chapter 2, the beginning system of linear algebraic equation. And so let me go to the content, and so we will basically today talk about this part of the book. So I plan to cover this book, all of this book, and I also plan to use other books which will supplement and enrich the content of the course, so that all the lectures, after watching all these lectures, you will be very deeply familiar with all the numerical methods and basic implementations of them in Python. So let's go to the code and see how it works. So first we will talk about Gauss elimination method. Gauss elimination method is, as you all of you may know, there is a matrix system which has the shape like let me put it as a command like this. So this is a matrix system. Okay, that's here. So from here we would like to x is unknown, x vector or matrix is unknown, and we have A and B matrices, and from this we should find x. So to find x, we do Gauss elimination method on A and B. So while we do it on A, we convert B and we reach to the solution of x. So just to refresh you how it works, let me show you an example here from the book. So if there's a matrix A like this in this form, and B is this, they're written just put together in one place. And from here you will the first step will be multiplying the first row by some factors and add it on the second row element by element, and also multiply it by some factor, and element by element, I mean this -2 multiplied by some number on this, and 1 multiplied by the same number on this, added on this. So we will do that, and we will come here, and from here we will multiply second row by some number and add on top of this. Then we will arrive in this form. So it will be just like 3 equations, but in matrix form. That's simple. So this is how a Gauss elimination method works. So once we have this form, you can just then substitute. For example, if it's x3, then you will get x3 equal to 9 divided by 3. So that's how it's work, to remind. And here is the implementation. So since we will go through each row from first row to last row, also we will go through each column, so that we multiply each column by relevant number. So here we get the number of row counting the B, number of rows here, and we here K and I, we have 2 loops, and this goes through each row and each column. So k is going through columns and i's are going through rows. So from 0 column or first column to last column, and then for each column element we go through rows which are one index higher. So let's talk about how it's implemented. So from 0 k and 1 I, so otherwise the first one will be, this one will be 1 and this will be 0. So 1 is already second row. So we come to this matrix and see second row and first column, and if it is not equal to 0, then we will do the operation. So what kind of operation is that? So we will first, this k is, as you know, 0. So first column and first row element, so this is 4, and the element first second row and first column, so this element. So we divide this element by this, and we get a multiplier. So with this multiplier, now we should multiply all elements of this and add them, each of them on top of, add to this values. So this is here. So from I, this is second row, as you know, from second column to last column. So from this from this and these guys will be are here and here, and we multiply this first guy, this is here, this k is here, k1 is this, so k or first row and k1, and then this is this two, because first case has value 0 in the first loop, so 0 and 1 to n. 1 is already the second column, so first row and second column. So we multiply these two guys from that multiplier, which is division of this by this. Then we add each of them one by one on top of this. Here these are these two, and we define these two as with new value. So it will be already added and it will be changed. So this is it. And for a k itself, we know that because once it's multiplied by this and multiplied, we will divide this by 4 and multiply that number by 4 and add this. Here we will get 0. Because we are aiming to 0, we don't need to do that operation. We could have done it here, like instead of k11, k plus 1, we could put k, then that will do the operation, but we just simply can define that element to be 0 here. No need to calculate. And for b it's similar for given I or row element. So for this minus 16, we update it by subtracting from it this multiplier multiplied by this k element, or here 11, for example. So this is the first pass when k has we are concerning first column element to be 0, and for I we just talked about the second row. then the next step of the for loop will be going down to this and multiplying these two guys by the multiplier and adding on top this, and the multiplier itself actually will change because we will shift I by 1, then it will be this guy 1, and the multiplier changed, then these values will be changed. So after this loop finishes, actually we come to this point. So from this point we will divide this guy by this and we will get x3, then substitute here and multiply the x3 value by this and put it on the other side of the equation and we will get x2. So this we call back substitution pass. So for this, as you can see, from last row to the last first row, we go one by one up or backward, like from down up, and for each of them we will replace b, update b by this is multiplication of matrix and b dot m, and this is we are multiplying. So each of the elements b which are below by elements in the a, corresponding elements in the a, and divide them by b. So what it does is, if you see carefully, you here you will have no b, which if we are talking about k, then there will be k will be in this 3 case, 3 dimension case, it will be 3, and there will be no 4b. Thus it will have no value, and since this will have empty value and this a will be empty valued, so this part will be empty. So this the value of b, last b will be b divided by the a. So this will be this 9 divided by 3. For the when we go up one level k to this, it puts b here, this is here, and this is multiplies the b's which are below this b. So if you are talking about this b, we will have a look at b here, which is below, and we already defined that to be this guy 9 divided by 3, or otherwise b, last b will be 3. So we will multiply that b here. If you see, it will be that could be same row and rows which are after this second row or bk row itself. So this will be multiplied by value of b here, which will be 3, and it will be subtracted. Then we will divide by the value 3. So basically it's just replacing value 3 here and multiplying by this guy, and we are subtracting this from here. Then we are dividing the result by 3, which is here. Then we get what we want. So for this same, this 2 will be divided by 2 b's here, but not this 10 point or 9. It will be the results of b's. Then we will multiply them here and subtract from here, and we will divide by 4, and we will get the b values. So it's a little bit complicated to explain, but the calculation is this simple, just a few lines of loops, and we get the result. So let's just have an example. I will define this function, and let's just cut in. And what we have in A is this. So, and what we have here is B is B this. So instead of this first 3 matrix, we have here an example of this matrix, and instead of these 3 guys, we have this B. And so now we will plug in this B and A matrix. So B doesn't need to be row or column, because in this loop it doesn't matter. It's just row or column. We will select, if you see here, select B by just one index. So it doesn't matter whether it's column or row. Yeah. And if we run our function, oh yeah, actually here I have an example. Gauss elim AB, then we will get the returned value will be already A and B. B will be, as you see here, we did the back substitution pass, because then B will be the already solution. So it's a little bit misleading to name them as this one. And A will be already back substitution. So this A will not be substituted. Sorry, B will be already the solution, and A will be this matrix, upper triangular matrix. So let's have a look. A solves. So we can see that it's an upper triangular matrix, and B solve will be already the solution. Solution is 1, 1, 1. So otherwise, if we say that this is for x1, this is for x2, this is x3, then each of them 1, 1, 1. And if we substitute, then this multiplied by 1, this multiplied by 1, this multiplied by 1, and sum of them will be equal to 6. So yeah, if you calculate, it is indeed 6, and sum of this indeed 5. Yeah, so it matches. So the calculation is correct. So we can confirm the correctness of the calculation by using Numpy's built-in inverse function. So basically, usually we solve this system by calculating x equal to inverse of A minus 1. Yeah, let's say minus 1, or let's say just inverse of A multiplied by B. It's matrix multiplication. So we just calculate, we can calculate as this, but algorithmically it takes more steps. So Gauss elimination can be much faster, and so if you can confirm the correctness of value by calculating like this. So here we can use A and B and do the calculation. However, there will be an issue. Show B solve. B solve will be already the solution. Yeah? The solution is different. So why we put same thing and we expect the same value as 1 and 1, 1, 1, but with different value? That's because if you have a look at our A and B, which are, if you see, it's similar to A solve, and B is already changed, but we expected them to be as this originally. Yeah? So in this user-defined functions, we manipulate A and B, and they are already in the global environment, so they are already changed. So A and B are changed. So even we just they don't need to be here named A or B. They can have different names in the function, but if we just plug our variables into function, it will do all the operations and our variables will be changed. So we should redefine the variables, and we redefined. Now we have a proper A, B, which you can use to calculate the correct solution. So we solved 1, we expected 1, 1, 1. Yeah, yes. So our this calculation with inverse matrix this confirms our calculation which uses Gauss elimination method. So this is correct. So this was an example of how to implement linear algebraic solution in Python. It's just using loop in matrix numpy array. Yeah. So this was the first example. So the second way of solving the system, same system, Ax and B, is to use a lower and upper decomposition, triangular decomposition. We call it LU decomposition, and the most common way to decompose is Doolittle's way. And in Doolittle's solution, we just and by a lower and upper triangular way, I mean, let's have a look at it from the book. So LU decomposition. So basically, the A matrix, there's matrix A, and that will be decomposed into two matrices. And if you multiply this lower triangular matrix with upper triangular matrix, then we will get A. And that's why we need to do that is if we here we can talk, here it's some implementation solution of the matrix. So if you have AXB function linear system like this, we can turn them into LU XB. Yeah, this is equivalent. LU is just A, and we can assume that UX as Y. Then in this case we have lower triangular matrix. So for triangular matrix, it's very easy to find solution. In this case, it will be just x1 multiplied 1 by 1, or in this case y, y multiplied by 1 equal to some b1. Okay, so we will do this substitutions. We will find value of this, then we will substitute here, then we will get value of this, then we will substitute here. Then once we calculate and find values of y's, we can equate y2 with upper triangular matrix and x, that x we are searching for. And for upper triangular matrix, we know from Gauss elimination method how to do this very easily. It's the same way as in lower triangular matrix. So both lower and upper triangular matrices are very easy to make a calculation. We just multiply, divide. So that's the motivation for using LU decomposition. So LU decomposition, there can be many different kind of LU decompositions depending on how the resulting matrices look like and what kind of properties they have. This most common way that I mentioned is Doolittle's way method, and the resulting equation, the matrix will look like this. Lower triangular matrix will be 1 1 1. It has 1 in the diagonal, main diagonal. So the only distinguishing factor is that. So then the next question is, how do we get this LU? Well, it's from a matrix A. So this is, if we just multiply them, this value as symbols, then if we just multiply this by this, then the resulting A matrix will be this. And from here we can I assume that we know A matrix itself. So U1 1 1, or this one will be equal to A1 1, right? So from this tree we can find easily the values of upper triangular matrix. So once we know this, we can substitute it here and we can get the value of this guy. Yeah? So in this way we can find each of the elements of lower and upper triangular matrix. So one interesting thing is if you see here, if A matrix is like this, and if you decompose or do Gauss elimination here, and so you will need to multiply this by L 2.121, and multiply this by L to 3, yeah, and then after that you will have this matrix. You can see the calculation, do the calculation here, and you can get this matrix, and from here to make it 0 you will get L, multiply this by L to 3, and you will get this. So the property you have to easily find is that when you have a matrix, you just do this Gauss elimination. Then from Gauss elimination you will find from the multipliers, you will get the values of L2, 3, and this guys. And then using these guys, you can also easily, you can use them to find the values of this upper triangular matrix. And usually we write upper and lower triangular matrix as this. We ignore these ones in the main diagonal and just put them together just to save some space. It's nothing to do with the numbers and calculations. It's just to save some space. And implementation of the code is here in the book. I just did it, followed or copied the same function in Python here. So what it does is, okay, let's go back to the book and let me talk more explicit about how it is handled. We can explain. Go to the Python code so we can understand, we can see how it works. So, as in the case with Gauss elimination method, we have a matrix, which is our matrix, A matrix, and we would like to decompose it into lower and upper triangular parts. So we find number of elements. So all these matrices, by the way, should be quadratic. So equal sign, end-to-end matrices. So this is size of row or size of column, that matter. Then we go through each column, then each row below the column, and we check the same condition, and we do the same multiplication, and we do the same things. So however, what we we do this Gauss elimination method, and the resulting Gauss matrix which is upper triangular is the upper triangular matrix of two-little LU decomposition. So in the lower triangular matrix, I thought this will be the multipliers. So if you remember from the previous Gauss elimination method, this multiplier is here. Then we just, instead of putting these values or these values to 0, we just put there our multipliers here, like this. So the resulting function will be like this. And we will get the so we from the things we do here, we just get this matrix, which is combination of lower and upper triangular matrices, and from here we can get the upper triangular and lower triangular matrices themselves. So for that we just copy on A to L for lower, U for upper matrix. So the reason why we do copy instead of just A equal to L equal to N is that if we copy, then if we change matrix L, A will not be changed. However, if we just say it's equal, then if we change L, the A will be changed following L. So that's not what we want. So we define LU as just same as this A matrix. This A matrix, to say again, it's like this, lower and upper matrix together, and from here just we define both of them as similar, and we will go through each of their column and row. Then we put values 0 that we want to be 0 for lower triangle matrix. We want the elements beyond the corresponding row or columns, which is to the right side. So if we are talking about second row, then we are talking about third and beyond, columns beyond. So this and others should be 0. So for the second row it's this, for first row it is here, and then second and third rows will be 0, and the diagonal elements will be 1. And for the upper triangle matrix, so for second row the columns until second column will be 0, and the same for third row. So these are done here, and then we return LU as function value. So then once we get LU decomposition, we can use it to solve the system. We can solve L using LU and B. The original system is, as I told before, AXB. Yeah? So we are just decomposing A into LU part. Now we can use all of this to calculate the value of X. For that purpose, it's simple. This backward substitution, this is the forward substitution, which is done for here in lower triangular function. So we will just from here, as I talked before, yeah? From here we will get a value of x1. What it will be equal to is lower triangular matrix multiplied by y's. This will be equal to b. So this will be here, and then our B matrix will be here. From here we will get y1. We will put y1 here, and we get y2, and here y3 using y1 and y2 here. Then once we get y's as shown in this equation, then we can use this resulting y values. There will be some values, yeah? Put them here, and we can just use it to find x's from upper triangular matrix backward substitution. So here is just backwards this forward substitution we call, and here solution of this equation we call backward substitution. This is exactly the same as the one we did for Gauss elimination back substitution pass here. So for this case, this is just going from up and down, but for this case it's going from down and up. The only difference is that it's simple. And then the resulting matrix will be B, which will be already our X. So let's define these two functions and see how they work. So our example 2 will be about lower and upper triangular decomposition. It's 2 littles way. And so there is built-in Scipy Python package, Scipy's built-in lower and upper triangular decomposition in Scipy's linear algebra module. And so we can decompose our A into lower and upper triangular matrix using this. This, however, will not give the same result as our this decomposition, because this uses something called pivoting, and pivoting means before we go from top to bottom and we make Gauss elimination and we find L and U matrices. Okay? So to do that, they just to pivoting means you put the row or call the row. So if you are here, if you are here, where is our A matrix? Okay, we can talk on an example. So let's define our A matrix here. So here, if you are working on this, and if you make this matrix upper triangular using Gauss elimination, then for this pivoting case we put this maximum value. So first we are working on first column, so we put this maximum value on the top row, and then put this row which was here to the place of that row, and then we do the Gauss elimination. And after we do for first column, then we will compare values of these two columns, and we will put the higher one on the second place, the other one on the third place. We will just replace the rows. Yeah. So this is done. This is useful because if you have higher value here, then you will need to multiply these values by smaller values to come to this value. For example, if 7 is on the first row, then to make it -3 and that, so you would divide it by -3 divided by 7, which is below 1. So when you multiply numbers by some smaller number, there will be less error approximation error, numerical error. Yeah. So that's why they use pivoting. So let's see how it does. So I just S is for Scipy, so US and LS. So this is, as you see here, this is the third row which is here, and you know that the upper triangular is just the one after Gauss elimination, and these numbers are the multipliers which are supposed to be always below 1, because we put a higher value on top and multiply that value by something lower than 1, and we get to this lower triangular matrix, or this Gauss eliminated upper triangular matrix. So values of this lower triangular matrix will be always 0 except 1 on the main diagonal and none lower than 1 in absolute value on other elements in the lower part of the matrix. So this is the result, and this we have, if you noticed here, we have P, which is pivoting. How pivoting was done, it has information. So it is here. So if we put a third row on to the first, and first to the second, and second to the third. If you put them like this, switch the original matrix like this, and do the pivoting, we don't need to do this row change. It will be just automatic. So let's see. MP dot means matrix multiplication, and let's try to multiply lower and upper triangular matrices, and it should, if there was no pivoting, it should give us the matrix A. But as you can see, the orders of this original matrix are changed, and you can see that as it's suggested here. Here it says it's like if it's one matrix, unit matrix, then it should the third should be on first, and this two should be shifted downward. So this should be in the first. This go up, and this two just shift down. Yeah. and actually the relationship should be, for this case, let's write here, it should be lower upper triangular matrix multiplication and PA, right? So let's see, and P dot P and our matrix A. So here we have, this is not really what we have from multiplication of these guys. Let me log interesting. How come? Oh no, it was not. Oh yeah, so what we get is this. So this is inner A, or if we just from the beginning did a little bit LUSS, yeah, and if we multiply that one by P, then we should come to our original matrix A. Yes, so that's how we get it. So pivoting, it's handled differently on different books, so I didn't notice it correctly. So pivoting will be like this: pivoting LU, then A. No? So that's how it's done. And for our function we defined here, these functions are, we don't need to use them actually, because we can get the values anyway. But however, depending on pivoting, lower and upper triangular matrix can be different. So this is just for illustration how these things can be done. And so let's see what they will show. So what we have in A. This is the matrix here, and let's do the decomposition. We just click F9 and L and U, which are, this is lower triangular and which has zeros here, ones on the main diagonal, but however some different values here. And this is our triangular matrix, and this is just without pivoting. Just here you see the first row, it's still there. And so we just decompose it into LU. Just to make sure it's correct, we multiply these two guys back, and we get the A matrix back. So now we knew A and B. So from here we want to find X. So solution X. My solo does the job. So let's put LU and B into my solo function, and let's find the solution. From previous example, we already know the solution. It should be 1 and 1, yeah? 1, 1, 1. Yes, it's the same solution as we found by using Gauss elimination method. So to solve the linear system, we can use Gauss elimination method or lower and upper triangular decomposition of Doolittle, which is most popular. And the next is to solve the same system. However, we will in this time use decomposition called Cholesky's decomposition. This is also lower and upper triangular decomposition, so it means A matrix will be decomposed into two, one of which will be lower and one which will be upper, and multiplication of these two. And so this is done. I will show some interesting notes from the book. Cholesky's decomposition. Cholesky decomposition. So Cholesky decomposition assumes that the A matrix should be symmetric. So transposing this A matrix will give exactly the same matrix. and the resulting lower and upper triangular matrix will be also transpose of each other. Transpose of lower triangular will be transpose the upper triangular matrix itself. So this L32 will be equal to L here. And so how to solve them is we just multiply these two and we see here, and from comparing these two matrices we can find the values. So general logic is it's written here. So if you carefully see, every Aij's position here will be this multiplication, basically this Ij, I row and j column, and this will be going from k to j. So it will multiplication, this multiplication or this decomposition is this. So for this case, for example, it will be I22 will be in any matrix multiplication of second row and second column. So it will be this multiplied by this multiplied by this, and yeah, and for this case, so for this case we can say 2 will be 2, and this will be 2. This is 2, 2, and you go from 1 and 2. K will be 1 and then 2. Here 1 and 2. So for the 2 case, so it will be 3, 3, 3, 3, 3, and for 2, however 1 and 2. So 1 and 2 is for j. J means column. The column's index. So from I and j is column, and k will be just from 1 to number of columns. In other words, if you are on the second column, you will have 2 elements. Third column, you will have 3 elements. Yes. And J 3, 1, 1. So for this case 1 and 3, for this case you will have multiplication of this 3 by this 3, and what you will get is only this 2. So this 2 will be missing. So because these two values will be 0, you don't get anything. And from here, so you will have this decomposition, or you can say this decomposition, and from here you can put out this diagonal element, the element. If you have Iij, and you can get Lij itself, and then you will have if you have Lj, it will be multiplied by Ljj, because it's, let's say, 3, 2. So this 3, 2 will be L32 will be L32 multiplied by this element. For example, for this case it will be this, and for this case it will be A21, it will be this. And for 2 1 will be actually, sorry, this will be multiplied by this guys, and this will be here. So this is multiplication of these two, and so you will get this sum. And so from here you can get this, extract this value and put all of the sum here and put this value out. And if general form will be like this, just you put this part into other side of the equation and divide it by this. However, if just I and g are equal, this will be quadratic, and for this case you can use this way, which is maybe a bit shorter than this. And so let's have a look how it's implemented. Just a little bit, the code will be the same in Python, of course, with different formula. How can we achieve? I can get the results. So to make sure that the matrix is symmetric, and it should be actually positive definite. Positive definite is linear combination, multiplication of this matrix by any given vector in the left hand side, and that's the same vectors transpose on the right hand side, and it will be positive. So positive definite means usually used for whereas the covariance matrix, which should have we should consist of positive values in general. So that's called some concept called positive definite, positive semi-definite they call. So to make sure that it's positive semi-definite, we can use this formula. So this is AKK. So for each column, a diagonal element, we subtract from this multiplication of the same row A's which are in the columns before that diagonal. So for example, we subtract from this, we subtract these two, this two to each raised to power, second power. So we are multiplying here, just same thing by itself. Then if this one is negative, then we cannot take square root. And so since we cannot take square root, or which we use for calculating, this is finding LJJ, yeah? So if we cannot take this square root, then the matrix, it means matrix is negative definite, and we cannot use. So once we get this square root of this diagonal elements, we then use it here for calculating each of the elements. So for this column and for this row, we go there, and as we saw this formula shows, we just do this calculation, and here this for the same row, right? So same row, and column will be the same. It's symmetric matrix, symmetric matrix, so transverse will be the same. So this is this column, but however it's this row here. Since symmetric, it doesn't matter, we use column or row index here, and the elements up to j, or in this case k, right? And we multiply them, divide, subtract a from a, and we divide actually it by this guy. So this guy is here. Why it's not a but LJJ is that we get LJJs from here, right? We get LJJs the elements on the diagonal here, then we just use them here. So it's used here, then we get A's, all of the A's, and just to make the matrix triangular, we put here the values which is below the main diagonal 0, and we get A. So let's see how it works. I'd use math function of Python. The A matrix, which the one we will use is this. This is given in the book. Let's have a look. This is, as you can see, this symmetric matrix, and B is just 4. And let's do Kolesky calculation here. Oh, yeah, I don't need to actually select. And this is L. Okay, this is our triangular matrix, and if we multiply it by its transpose, do we get our A back or not? Transpose. So here we get our A back. So this calculation seems to be correct. Yeah. Actually, this is making zeros on the rows which are up to the column number of them. So these two are made 0 in one loop of this, and these three are made 0 in the last loop of this, just to clarify. And so Kolesky is working, and L multiplied by transpose of it gives the same value, same A back. Now let's use NumPy's built-in Kolesky. So we will call it L and P. So let's have a look. A is already changed because we used them here. So let's define A. Instead of always defining it, you can use this A copy thing just to use my X will be my CC or some variable will be equal to copy it, so it will be detached from A. If you change CC, it will not affect A, but I think it's for clarity, it's better to use like again and again. And let's have a look the resulting, or using built-in functions don't affect. So we have law for triangular matrix, which is similar to what we got using our user-defined function, this function, I mean. And so now we Cholesky decompose, and our final aim is to find a solution to the linear system, right? And A and B. Now let's try to solve the system A and B by inverse matrix method. So let's say the solution is B solve 1 equal to. So the solution is this. Now if we use our Kolesky decomposition, how it will look. L, find out L, then use it's my solver is, as you know, lower and upper triangular matrices are used. So lower is L, upper will be L transpose M, and B solve will be just the same as the one we found by using inverse matrix method. So that's it. So why we need to use this lower triangular, upper triangular matrix and Gaussian elimination is even when we have this inverse matrix method, is that they just in larger applications they just take time, and they can be used in many ways, many complex problems. It makes it easy to understand. Inverse matrix method is just too complex to understand what's going on. Yeah. So that was it, and that's how we solve linear equations, and we will continue in the next next lesson with this other iterative method, and we will continue with other methods of solving linear algebraic system or questions. So thank you very much for your attention. See you.